Hey y'all, we are going to finish 5.2, which is systems of linear equations in three variables. We have learned how to show if a solution set is the actual solution set. We have solved a given system. We just identified the different equations, kind of work within the equations. You need to know that your goal is to solve for variables, and then once you solve for one, you can use that to solve for another one, so on and so forth. I usually try my best to label each new equation and kind of explain the step that's going on to hopefully have some clarity in what it is that we're doing. Our goal, of course, in a system of equations that's in three variables is that we solve for three variables, which would be our ordered triple. If you get to an answer and you're not too sure if you're correct, you would simply just plug that solution set, right, that ordered triple, into the original problem, solving each individual one, right, plugging in all three variables and solving each individual one. You should get true statements, which means that it is the solution set to that system of equations. Okay, so let's go ahead and do this second example right here. If you notice the way it's written already kind of looks a little different. That first equation is just a negative 3x negative y equals negative 10. There's not a z variable. They actually kind of help out a little bit by putting it the way that it is, right? And then the second equation is missing an x variable. Third equation has all. This should help highlight the fact that I could not use equation 1. Let me go and number these. Let me flip my laptop real quick. This should mean that you should notice that our first equation, which is what we're going to label equation 1 one day, sooner or later, we'll get to it. Our first equation, our second, and our third, right? You should notice that I could not use equation 1 to solve for the z variable in equation 3 because I don't even have a z in equation 1 to be able to solve for the z in equation 3, right? Like I wouldn't use those, okay? What I do notice though is, well, also equation 2 doesn't have an x, so I wouldn't use that one to, pair with equation 1 or equation 3. What I do notice is that equation 1 and equation 3 both have an x. So I actually want to focus on those, do what I need to do to one of the equations so that when I do my next step, which would be combining them, I know that what I will end up doing is just kind of like getting rid of that variable, if that makes any sense. If you look at equation 1, I have a negative 3 as the coefficient on that variable. If you look at equation 3, I've got a positive 1 as the coefficient on that variable, right? We're looking at the x. So I need to think about what could I do to one of those equations that when I combine to the other one, it would give me that additive inverse that I'm looking for, right? So I know that since the coefficient on the leading term in equation 1 is a negative 3, I would combine that with a positive 3, correct? And so what I actually am going to do is let me see. I was going to just do this. I don't know if that would not really explain what I'm doing though. I'm going to multiply a positive 3 with my equation 3. Okay, so let's go ahead and do that. Let's call it a new equation, and then let's see what we can do with that first equation to kind of combine them together. Now, what I would have is, work in purple, the number 3 multiplied with equation 3. And with a negative 4. I'm literally, because it's touching a parenthesis, that implies multiplication. And I'm going to distribute it to every single term. What I get is 3 times x is 3x. 3 times 4 is 12. Signs are different, so it's negative. No y times y is still just y. 3 times 1 is 3. Signs are the same, so it's positive. No z times z is still z. equals 3 times 4 is 12. Signs are different, so it's negative. And I'm going to go ahead and label this equation 4. And what I'm going to do is I'm going to notice that if I combine, right, equation 4 with equation 1, that's going to mean that I have additive inverses for those variables. So let me go ahead and put my steps here. We're going to combine equation 1 with equation 4. So if I write equation 1, I have negative 3x negative y. I just have like a little space here. This is literally just so that I can have my like terms lined up with each other. My equation 4 is going to be a 3x. That's a negative 12y. That's a positive 3z equals a negative 12. I need to change the TV. I had no idea what time it was today. Just something that's not that. Everything wants codes. Okay, so let's go ahead and combine both of these together. If you look at those first two terms, same exact terms, different signs, additive inverses, they cancel. Look at your y terms. Those are the same signs, right? That's a 1 and a 12. Well, because they're the same sign, what you do is you just add your values, keep your sign, keep your variable, keep your exponent, right? Then right here, I have a positive 3z combined with nothing, which is just a positive 3z equals, if you combine a negative 10 and a negative 12, because the signs are the same, you just add them together and you keep the sign. Okay, so if I thought, oh, wow, okay, I can go ahead and solve for z or solve for y, and you actually start doing those steps, when you get to that last step, which is, dividing by the coefficient on the variable you're trying to solve for, you're going to notice you're looking at a pretty ugly fraction. That would mean that you actually can just stop right here. There's no reason to move forward anymore. That is a perfectly fine equation to call number 5. And, let's see what else we can do. Okay, so what we're going to do is we're actually going to look at this new equation that we have, and we're going to look also at our original equations, and I'm going to see if there's anything here that I could do. The fact that they both are just solved for y and z, and neither of them have x's, means that I could go ahead and I could use substitution, right? So let's go ahead and do that. That was equation 2 and equation 5. So we're going to use the substitution method, substitution method, and this is going to be with equation 2 and equation 5. Just to explain why again, equation 5, I only have a y and a z variable. Equation 2, I only have a y and a z variable. I couldn't do this method with 5 and 1 because they don't have the exact same variables. I couldn't do it with 5 and 3 because they don't have the exact same variables. I couldn't do pretty much anything with 1, 2, and 3 except for kind of cancel one of the variables, and I've already done that, right? So because I noticed that equation 2, let me see my work in purple, that's a y minus 4z equals 13. I'm gonna throw my laptop. It's gonna happen. I literally can't stand it when it does that. I don't even know why it does it. Y minus 4z equals, I usually like 54. I didn't know I wrote that big. We'll say here, equals 13, right? Was it 13? Yeah. And we're going to actually use the substitution method with the 5th equation, which is a negative 13y positive 3z equals a negative 22. I can do this. This is technically me taking advantage of the fact that this looks a lot like 5.1, and I know how to solve problems that are in 5.1, so I'm doing that now that I see that, okay? So I would want to grab one of these equations and I'm going to actually solve it for a variable. Now, just to keep things clear, this is equation 2, right? And then this is equation 5. 5 right now is my largest that I have. I actually want to use equation 2 and I want to solve for my y, right? Because there's no coefficient on my y. That's going to be the easiest one to do. So I'm going to solve equation 2 for y. And this will actually give me my 6th equation. So what I get is y negative 4z equals 13. I would move that over and I would get 4z. That's a positive 13. So this is a new equation. Call it equation 6. Y'all, once you notice that what you're doing is substitution method as far as calling them and, calling a new equation a new number, if you know the steps and you know why you're doing it and you know where to go, the calling all of these by specific numbered equations isn't completely necessary, okay? It's when you don't and you're trying to keep things clear and you just want to make sure you don't mess up and, you have your directions and you're trying to follow them perfectly right. That's when you might want to label stuff, okay? So this y equals 4z and then a positive 13. What I'm going to do is I'm actually going to plug it into equation 5, right? Because this is where I'm doing my substitution work. So I'm going to plug my equation 6 into equation 5. Technically what I'm doing is just replacing the y value, right? So I get a negative 13 open. My y I just now found to be 4z positive 13 close plus 3z equals a negative 22. Now, if you notice here, all that I have is just one variable, which is great because that means that I can actually go ahead and solve for z, right? Here I had two variables. I couldn't just solve for y, right? I've got an expression because I have two variables. But my goal is still trying to get to x equals or y equals or z equals, okay? So let's go ahead and what we're going to do is distribute this 13 into that binomial. If you do 13 times 4, what you get is 52. Signs are different, so it's negative. No z times z is z, right? Like don't forget that variable. And then if you do 13, I saw it. I see it. Sorry. That expression, y'all, y is actually 4z plus 13. Thank you. Okay, so if you do the multiplication of 13 times 13, you get 169. Signs are different, so it's negative. I've got plus 3z equals a negative 22. Let's go ahead and combine like terms. I've got a negative 52z and a positive 3z. Because signs are different, what you do is you subtract, keep the sign of the larger, keep your variable, keep your exponent. If y'all are okay with it, that's a negative 169. I'm actually going to make it a positive 169 on both sides, right? Cancels on the left. Over here, signs would be different. I would subtract, keep the sign of the larger. And then last step, if you divide both sides by a negative 49, what you get is z equals a negative 3. Okay, so this is going to be my star. That is going to be the answer for the variable of z. Now, what I want to do is look back at where I was doing my substitution, which is right here. Okay, so what I'm going to do is actually, how much room did I give myself for this problem? Not enough. Delete that. What I'm going to do is actually plug the z into one of the equations in here to solve for not z, but y, right? This is the easiest one, so it's the one that I'm going to use, okay? And so let me go ahead and write my notes. We're going to plug z into equation 2. Okay, and this is using the two equations that I'm doing substitution within them. Okay, I haven't gone back to an original yet. So equation 2 is y minus 4z equals 13. Actually, honestly, y'all, look, you can plug it in here. You can plug it in here, but I think the actual rule would be to plug it into one of the originals that you're doing the substitution on. Okay, so let's just go and do it. So what you get is purple, y, and then we have minus 4 open times a negative 3 close, and then we have a positive. Why did I do that? I said y. Y minus 4z equals 13. Y minus 4z, yeah, equals 13. It was that last part I messed up on. Okay, so what I notice here is I have my y. For the 4 and the 3, it's multiplication, right? The signs are different, but first let's look at my coefficients. 4 times 3 is 12. Signs are the same. Look, I messed up. Signs are the same, so it's positive equals 13. I actually want to subtract 12 from both sides, and what I would get is y equals 1. So we're just going to go in. We got one called star, one called little asterisk. Let's move up. Okay, now that I have solved for a z and a y, what I can do is plug both of these variables into an original. Okay, so we're going to plug star and the asterisk, right? Those are my two variables I solved for, into an original equation. We're going to plug both of those values I just solved for into an original equation. Looking at my equations, I know that since I have my star and my asterisk is z and y, so this is z and y, I need to solve for my x, right? So I want to make sure that I at least plug it into an original that has an x. I picked the third equation, because I liked the fact that x doesn't have a coefficient on it, and because I know since I'm plugging in a z, equation 1 doesn't have a z. So that's kind of my train of thought there, okay? And so what I do is I'm going to pick equation 3, and what I have is x, and then we have a negative 4 times y. My y is a 1. And then we have a positive z, right? So a positive z, but my z is actually a negative 3, and then equal, I've got a negative 4. So I've got x, 4 times 1 is 4, signs are different, so it's negative. This would be a 1, right? 1 times 3 is 3, signs are different, so it's a negative, equals a negative 4. And then on the left-hand side, those signs are the same, so you would add them and you would keep the sign. And then if I move that negative 7 over, it becomes positive. So I would have signs are different. You subtract, keep the sign a bit larger. What I get here for dot is that x equals 3. My ordered triple is actually going to be comprised of my x, y, and z, which were dot, asterisk, and star, because I stopped labeling them by, 6, 7, 8, 9. You can only have so many equations in one problem, Okay, so what I would do, not that, is list 3, and then we have a 1, and then we have a negative 3. Whew, that is going to be the ordered triple for that system of equations, which means this is the solution set. Like I said before, if you wanted to go back and plug it in, you can. Y'all, we actually have one more problem for this section. I'm going to do it on its own video, though. Let me look at it real quick. Yeah, I'm going to do it on its own video, okay? So if y'all have any questions, make sure you let me know. Thanks.